Hello, I'm Roman and welcome back to the series of the videos Neural Networks from Scratch in Go, where we dive into the bare bones what is the neural network is and how it works. I'm using this book called Neural Networks from Scratch in Python, but again, as you can guess, I'm writing everything in the Go. And in the previous video, I recreated the vertical data function that returns something like this. Let's take a look again that it still works. Yeah, so the distribution is a little bit different, but I think that's okay. So we have 3 different samples for the points, and what we're doing right now is we are actually on the chapter 6, introducing optimization, and this is where I stopped. The only thing that I want to do before we go next is to do a little bit of name changes. So here I would call it the same, like dance 1, dance 2, activation 1, activation 2. So let's take on layer 1, dance 1, then rel 1, it should be activation, then second layer should be dance 2. And I think the last one is the softmax. It's activation 2. Okay. Did I make a mistake? No. Okay. So right now, I think from here we're going to do some optimizations. So we're taking, okay. We're taking the lowest loss as some big value, and I'm thinking the loss returns me float 64, so or do I have something like max? Max float? Max float 64. Max float 4. Where is it? It's in the math. So we have the. Then I think what we're going to store is weights and biases. And initially we need to copy them from the layers that we have. Best dance 1 weights. Right now I need to make a copy of weights Can I? D. Maybe I need to pre-allocate it. And then copy values into this math new dense. And copy. Okay. Then we have biases. Same. Right. And I need to do the same for the second one. Okay. Then create some variables to track the best loss and associated weights and biases. We initialize the loss to a large value and will decrease it when a new lower loss is found. We are also copying weights and biases. Copy ensures a full copy instead of reference to the object. It returns a newly allocated copy. So that's what I need. Now we iterate as many times as desired, pick random values for weights and biases, and save the weights and biases if they generate the lowest seen loss. Okay. Or how many times? 10. So what we're doing, we need to generate new. We need to generate new. That's one weights. Don't need this. Clear this. Okay, I need a function that will make this randomization. I will move it into main for now. Oops. And that should return the new dense, right? Okay. Func random values int and it returns dense in my case. Random Okay, the number. Array. And then we initialize it to random. What was the value? Numpy random dot rand n. This one. Returns a sample of from standard normal distribution. So it could return any number. So I think this one is okay. The only thing we need to multiply it by this one. And then see. Oh, math, rent. Okay. So we initialize this. Then biases. No. Then one biases. And then we're doing the same for the second. Right? Okay, then we go in using forward. We're actually going through the network. We're taking the first, then we using the first activation, then we using the second layer, then we using the second activation, right? Inputs, taking the output, okay. Then we calculating the loss, this one. Perform a forward pass-through activation function takes the output of the second and layer here and returns loss. Then we calculate accuracy again, so doing this. Okay. If the loss is smaller, so if loss value is less than lowest loss, New set of weights found. Iteration I loss value accuracy So lowest loss equals to loss value, and then I need to copy but what's loss urgent falls but not urgent first. Oh, so we're just trying to find so we're not decreasing it, we're just trying to find the best one. Okay. So we're just doing this once again. Which, okay. What do you mean it's declared but not used? I'm using it here. Oh, it's like it's still considered as not used. Oh, no. But okay. Okay. Best stance weight. I don't know. Dims, but I think I cannot read dims. Oh no, I can. Just to fulfill the compiler. No, you cannot. Okay. It's not used. Okay, let's. Okay, so it finds the sets with the smaller loss but the accuracy didn't change much. Loss certainly falls through, not by much. Accuracy did not improve except for a singular situation where the model randomly found a set of weights yielding better accuracy. But I didn't have this. Oh yeah, I had it once here. Oh. Loss continued to drop, but accuracy didn't change. This doesn't appear to be a reliable method for minimizing loss. After running for 1 billion iterations, the following was the best result. Okay. Even with the basic dataset, we see that randomly searching for weight and bias combination will take far too long to be acceptable method. Another idea might be, instead of setting parameters with randomly chosen values each iteration, apply a fraction of these values to parameters. With this, weights will be updated from what currently yields us lowest loss instead of aimlessly randomly. If the adjustment decreases loss, we'll make it the new point to adjust from. If loss instead increases due to adjustment, then we will revert to the previous point. Using similar code from earlier, we will first change from randomly selecting weights and biases to randomly adjust them. So this is okay, and maybe ads. We can use ads and take then swan weights, right? And then we do random values around C. Can use random values around C as mathematics value in the argument. Okay, what if I'll return the matrix? Add elements and be element-wise, placing the result into receiver. I'm just checking. Then 2 and 2. Okay, that should work. No, can't use maths. I give up. No, I just want to... like this. Okay, it doesn't fail, okay. And then we'll change our end if statement. So, okay, I need finally this. Right. Else I need to... What I need to take first layer, I need to take weights, and I need to do math, then copy off. And what I want here, I want best and weight. Well, it's actually training. Let's, I don't know. No, 10 times more. Interesting that the accuracy is not improving higher. Okay. The training session ended with almost no progress. Loss decreased slightly and accuracy is barely above the initial value. Later we will learn that the most probable reason for this is called a local minimum of loss. The data complexity is not irrelevant here. It turns out our problems are hard for a reason. And we need to approach this problem more intelligently. Smarter. Let's use the word smarter. Okay, so right now we're going to the chapter 7. Well, I have a lot to do here. I think where is no, not this one, table of content. Derivatives, this one, right? Interesting that it, from this perspective, I just spent 140, but it's like 1/3. Okay, let's take a look at the derivatives. I think I'm not sure that I'm going to implement this stuff. I'm just, checking through the code, because I think right now it will be an explanation of what the derivative is. Yeah, just quickly checking. So well, unless we will use some of these functions later, then I will implement some of them, but yeah, but it's mostly just math and gradients, partial derivatives, a chain rule. Okay. Yeah, I'm probably won't go to implement these functions to plot them. Randomly changing and searching for optimal weights and biases did not prove fruitful for one main reason. The number of possible combinations of weights and biases is infinite, and we need something smarter than pure luck to achieve any success. Each weight and bias may also have different degrees of influence on the loss. Yeah. This influence depends on the parameters themselves as well as the current sample, which is an input to the first layer. These input values are then multiplied by the weight, so the input data affects the neuron's output and affects the impact that weights make, because the idea that the neural network tries to fit the current batch, the current input, and even the same model, like the model architecture, will have different sets of the params, like weights and biases in the end, once you pass through the training data, because it really, the idea of the model is to kind of predict the output based on the given data set. The same principle applies to the bias parameter in the next layer, taking the previous layer's output as input. This means that the impact on the output value depends on the parameters as well as the samples, which is why we're calculating the loss value per each sample separately. Finally, the function of how a weight or bias impacts the overall loss is not necessarily linear, and we saw that before, I think, in the chapter inactivation functions, so how it actually alternates the weights. In order to know how to adjust weights and biases, we first need to understand their impact on the loss. One concept to note is that we refer to weights and biases as their impact on the loss function. The loss function doesn't contain weights or biases, though the input to this function is the output of the model, and weights and biases of neurons influence the output. Those, even though we calculate loss from the model's output, we calculate loss from the model's output, so the one that goes through the, for example, in this example, through the softmax activation function, right? So we calculate this kind of, well, I'm not saying that's derivative, but a side effect of the weights and biases. These weights and biases directly impact the loss. Yeah, because still the weights and biases form what will be the output. In the coming chapters, we'll describe exactly how this happens by explaining partial derivatives, gradients, gradient descent, and backpropagation. So I assume here we will start with more math than we had in the previous chapter, especially I think the next two chapters, like derivatives, gradients, and even the backpropagation, I believe. Or probably here we'll start writing some code. Here it will be more of the explanations. But we need to understand all of this in order to actually being able to, implement this. Basically, we will calculate how much each singular weight and bias. Basically, we will calculate how much each singular weight and bias changes the lost value. Singular weight. So basically, how each neuron contributes to the lost value. Given a sample, as each sample produces separate output, those also a separate loss, and how to change this weight or bias for the lost value to decrease. Remember, our goal here is to decrease loss, and we'll do this by using gradient descent. Gradient, on the other hand, is a result of the calculation of the partial derivatives, and we'll backpropagate it. Gradient, on the other hand, is the result of the calculation of the partial derivatives, and we'll backpropagate it using the chain rule to update all of the weights and biases. Don't worry if that doesn't make much sense yet. We'll explain all of these terms and how to perform this action in the coming chapter. So I think the idea is that we will after each iteration we'll calculate the contribution of each neuron to the loss, and then we will go from this loss change back to each weight and bias and adjust it based on its contribution. So for example, if one neuron contributes to the loss more than another, then it means that the difference of such neurons should be bigger, so we can, go faster in decreasing the loss. To understand partial derivatives, we need to start with the derivatives, which are the special case of the partial derivatives. They are calculated from a function taking a single parameter. Okay. I will stop for today. This video will be a little bit shorter, but yeah, I will continue tomorrow, and I think this will be mostly me diving into actually remembering again what a derivative is and how to calculate it, and I will, explain everything that I found here. So yeah, thank you for watching, and I see you tomorrow. Bye bye.